Problem 1 is very straightforward. Use a calculator to find the indicated values of the exponential function. Make sure they're correct to within 3 decimal places, so you just want to round correctly. Problem 2, we have 2 to the x. There's a negative in front of that x, which means that you reflect the graph across the y-axis because all the x values now are the opposite of what they originally were. The plus 1 means move the graph 1 unit to the left. You have to graph it without a calculator. Your domain, as you can see, is all real numbers, and the range is y is greater than 0, and the asymptote is y equals 0. Problem 9, we want to graph this without a calculator. Then log base 3 of x minus 1, the minus 1 moves it to the right, 1 unit. So the domain becomes x is greater than 1, the range is all real numbers, and the asymptote is x equals 1. Problem 13, we want to graph without a calculator. So it's e to the x, we know what that looks like, and we just want to subtract 1, which means move it down 1 unit. The domain becomes all real numbers. The range is y is greater than a negative 1. That's hard to see on this graph because notice that the scale is every block represents 1/2. So just make sure you read the scale properly. The range is y is greater than a negative 1, and the asymptote is y equals a negative 1. Problem 17, we're trying to determine what the domain of this function is. Remember, for domain, we're looking for allowable x values. In this problem, 10 to the x squared, x can be positive, negative, it doesn't matter. But the log presents a problem because the log only exists if the argument is greater than 0. Whatever you're taking the log of has to be greater than 0. So 1 minus 2x has to be greater than 0. Go ahead and solve that, and you get the domain as x is less than 1/2. Problem 21, we are writing that equation in exponential form. Remember, the base of the log is the base of the exponent. So 2 to the 10th equals 1024. Problem 25, we're writing in logarithmic form. The base of the exponent is the base of the log. Log base 2 of 64 equals 6. Problem 29, we are trying to solve for x. So we have I think it's helpful to put it in exponential form, and you have 2 to the x equals 128. So what is x? Well, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th, that's what gives you 128. So x must be 7. Problem 33, we are evaluating the expression without a calculator. We have the natural log of e to the 6th. We use our rule of exponents that says if you are taking the log of something to an exponent, you can bring that exponent out front and multiply it. So we have 6 natural log of e. Natural log of e is just 1. What power do you have to raise e to get e? 1. So that gives you 6 times 1, which is 6. Log base 5, problem 37, log base 5 is the square root of 5. You need to recognize that the square root is the same thing as raising to the 1/2 power. So we change that to 5 to the 1/2. Then we have our rule of logarithms, which says that if you have the log of something raised to a power, you can bring that power out front. So we have 1/2 times log base 5 of 5. And log base 5 of 5 is just 1, so it's 1/2. The answer is 1/2. Problem number 41. We are taking the log base 2 of 16 to the 23rd. Since the base of the log is 2, we need to put everything in terms of 2. So we need to change that 16 to 2 to the 4th. Our rules of exponents say that you multiply 4 times 23. That gives us 2 to the 92nd power. So what do you do when you have a log of something raised to an exponent? You bring that exponent out front, and we have 92 log base 2 of 2, which is just 1. So that gives us 92. Problem 45, we're expanding this using our rules of logarithms. The log of a product is the sum of the logs. So we break this up into the log of A plus the log of B squared plus the log of C cubed. And then we do our thing with our exponents. We bring our exponents out front and multiply. Problem 49 is kind of ugly. We have the log base 5 of x squared times 1 minus 5x to the 3 halves over the square root. Oh my gosh, that's a lot of stuff. We're multiplying. We can change our log of a product into the sum of the logs. So we can take that numerator and say, hey, that's log base 5 of x squared plus log base 5 of 1 minus 5x to the 3 halves. And then the log of the quotient, when you're dividing, you can subtract the logs. So that gives us minus the log base 5 of the square root of x cubed minus 3. Our exponent, 3 halves here with its 1 minus 5x. You can bring that out front and multiply it. And, of course, we know that the square root, we can change that to a 1 half exponent, which we can then bring out and multiply times log base 5 of x cubed minus x. So that gives us our expansion of the log. Now we want to put the log back together. In problem 53, we want to combine these to a single logarithm. Our numbers that are out front and multiplied, we can take and make exponents. So 3 halves becomes 3 halves exponent. 2 becomes squared exponent. We're subtracting these logs, and the difference of the logs is the log of the quotient. So we want to rewrite that as the log of x minus y to the 3 halves over x squared plus y squared squared. So we've combined that to make it a single logarithm. 57, we're trying to solve for x. There are different ways to do this. One way is just to take the log of both sides. So we have log base 10 of 3 to the 2x minus 7 equals log of 27. Now we use our rule of the log of something with an exponent. We bring that exponent out front. That gives us this log 3 and log 27. We'd like to get those together, so we divide both sides by log of 3. Log 27 over log 3, that's just the number 3. Okay? So 2x minus 7 equals 3. Add 7 to both sides, that gives us 2x equals 10. Divide both sides by 2, that gives us x equals 5. Problem 61, there are different ways to work it. One way is to take the logs of both sides. So we just take the log of both sides, we bring those exponents down, multiply through, that gives us log x minus x log 4 equals 2x log 3 plus 5 log 3. We need to get the x's on one side together, so I added x log x to both sides. I subtracted 5 log 3 from both sides. That gives us our terms without x's on the left and our terms with x's on the right. Factor out that x, you get 2 log 3 plus log 4. That's nice. Now we just have one x. We can divide both sides by 2 log 3 plus log 4, and that will give us this exact answer. X is log 4 minus 5 log 3 divided by the quantity 2 log 3 plus log 4. That's the exact answer. You can put that in your calculator. Be very careful. You might need to put parentheses around the top and both terms in the numerator. Put parentheses around the entire denominator. You should be able to get negative 1.15 equals x. This 65 that we're trying to solve, I don't like it in logarithmic form. So convert it to an exponential form. We get 2 to the 4th equals 1 minus x. And it's easy to solve. 2 to the 4th is 16. We can subtract 1 from both sides. That gives us 15 equals negative x. Multiply both sides by negative 1, and we get x equals negative 15. Problem 69. Gosh, I don't know. I can't solve it in exponential form. So we take the log of both sides. That gives us this second line here, where we have the log of 5 to the negative 2x over 3. I don't know about you, but I don't like having that negative 2x over 3 in the exponential form here. So I bring it down front and multiply it by log of 5. Then I divide both sides by log 5. I don't want negative 2/3 here, so I multiply both sides by negative 3/2. And that gives me x equals negative 3/2 log of 0.63 over log 5. Make sure you close your parentheses around that log when you're using your calculator. And if you do it correctly, you should be able to get x equals 0.430618. Problem 73. Be careful when you input that into the calculator, making sure that you use parentheses so that you're taking the 3 to the power that you want. You should get this graph. The asymptotes are y equals 2.72. You can use with your table, or you can find that with your table, or just changing the range. X equals negative 3 is the vertical asymptote. There is no maximum or minimum for this problem. Problem 77, we want to know where these equal. I graphed both of them, 3 log x, y equals 3 log x, I graphed that. I graphed y equals 6 minus 2x, that gave me these two lines. I want to know where the lines cross, and that happens at x equals 2.42. You can find that using your second button and calculate on your calculator and look for where those two lines intersect. Problem 89, we're calculating various amounts in an account. The amount invested is $12,000. The rate is 10%. The time is 3 years. But we want to change the way that we compound it. In our first problem, we're compounding semi-annually. That means twice a year. So n equals 2. Put that 2 into the equation. You have 0.1 over 2 and 2 times 3. Be careful with your calculation. You want, when you raise it to the power, you want it to be to the 6th power. You want to make sure that you calculate that 2 times 3 before you raise it to that exponent. You should be getting 16,081.15. If you compound it monthly, n is 12. Go through and calculate. Being careful, you might want to just raise it to the 36th power, or else put the 12 times 6 in parentheses. You should be getting 16,178.18. Part C. You now have 365 days a year that you're compounding it. You want to multiply that 365 times 3, or else put it in parentheses so that your calculator will do it correctly, and you should be getting 16,197.464. Then we want to compound continuously, so we have to use our PERT formula. We still have the same rate, and the time is 3 years. Put that in, you should get $1,698.31. So notice that compounding continuously gives you more money than either of the three other problems, because you're putting that money and earning interest on it as soon as you get it. Last problem, problem 91. We know that we're investing $100,000. We want to earn $10,000 in interest. That means the amount that we want in the account is $110,000. Our rate is 5.2%, and we're compounding it daily. So we put those into our formula. That gives us, calculating this 1 plus 0.052 over 365, we want to calculate that part of it. Go ahead and raise it to the 365th power, and that'll give us 1.05337181. Keep all of these decimals while you're calculating it. Don't round, because if you start rounding, like if you rounded this to 1, you wouldn't get the right answer at all. On the left-hand side, we've divided both sides by 100,000, and so that gives us 1.1. We have it in exponential form. Can't solve it. Take the log of both sides. We get this. divide both sides by, bring the t down,